We're going to do a few more of these little mini. There's so many possible estimation techniques out there, but good news, you've paid the fixed cost of learning R, so now you're going to see your investment really pay off. Going forward, you regularly read about some research project that uses what is essentially effing magic procedure. You have no idea what it is, but they say it's really good. Maybe a couple other people take it up. You say, wow, that sounds really impressive. Maybe they're really talented. They must know a lot. But the simple fact is that whatever effing magic they're doing, there's probably a package on R that does exactly it. And it probably has a similar kind of format to the LM call. A lot of packages are written that way. So you get the package, code it as usual, and then the main challenge is just to interpret some of the output. You don't have to know all the details. Now, I don't want to encourage you to just go off without understanding. Don't be a tool, but don't be intimidated either. Other people aren't better or smarter than you. There's no reason to believe their results just because they have some thing that you've never heard of. Don't believe it signals something more than, somebody figured out how to install another package in R. Great for them. So we usually take the data and split it into training set and a test set. The training set, as sounds, is we're training the model to recognize certain variation and associate certain bits of variation with certain outcomes. We estimate the model on the training set. Then we try it out on the test set, which we kept back, we didn't let the model see. That allows us to judge how well the model can explain new data. One of the common problems we get is procedures might overfit the training data and completely collapse when they're looking at new data. With some procedures, there's cross-validation where we take the training set and don't even use the whole training set, but use randomly selected parts of the training set to estimate the model. Do that in a bunch of different subsets of the training set to find the best parameters. So we're splitting the data multiple ways to estimate. That's completely demolishing any test of statistical significance. Our p-values are not at all accurate in this case. I first wrote that statistical significance cannot be used here, but then I realized that plenty of people do in fact use p-values even in these kinds of setup. They should not, however. Actually there's quite a lot of poking around before coming up with the final model, and so the p-value is completely inaccurate. Anyway, typical OLS regression we've been doing, maybe explain average outcome, the average predicted value conditional on the x variables. But we could be interested in predicting the median instead of the mean, or if the distribution is very skewed, maybe we're interested in tail outcomes. We could try to predict the 75th percentile or the 25th percentile or whatever other values. This chart shows income by age for workers with a 4-year degree to show the heteroscedasticity there that, the percentiles on the high end really go up, particularly as people get older, right? And so that gap, of course, is asymmetric as well. The lower percentiles are flat, the upper ones, rise quite a bit. That might be a good use for a quantile regression. Roger Conker is the statistician who figured out most of the details of that. It's, again, pretty computationally heavy. Recall back when we talked about OLS, there's a formula. X squared has a minimum value. That's pretty easy. But figuring out where the absolute value has a minimum rather than the squared value, that's tougher. But the computer can do that work. There's plenty going on underneath the formula, but for R, this is now easy. Instead of LM, we use RQ, which is regression quartile. Couldn't use QR because that's a term from linear algebra. No, Roger Conker, like Yoda, doesn't talk. In R, just set the percentiles we want to estimate, and then the rest of the syntax should look very familiar. Here's some of the results. You can see that it does a pretty good job of representing the spread of the outcomes there.